Hello guys, welcome back to another New Horizon Tutoring ACT video. Again, if you don't remember, my name is Liz. We're going to be going over, you guessed it, more math today. And it's actually going to build directly off what we learned last time, which is great, because a really big concept that you're going to see cropping up in ACT Math in either like all of the practice videos that we do, or just in your own practice, or within like some of the strategies that you read in, let's say, ACT books or online. It's just like the constant integration and application of these concepts that we learned. Because obviously this is all for the test. So if we aren't able to successfully apply the strategies and the rules and the formulas that we learn in class, it doesn't do us much good to have that knowledge, and even then, can we say that we really know it if we can't apply it? So that's what we're going to be doing today, which is awesome. So if you remember last time, we worked basically entirely out of page 8 of the ACT Math packet, which is essentially quadratic functions. So we were dealing with parabolas, transformations of parabolas, kind of how we can determine what the graph looks like, I guess, from the actual quadratic function that they give us. We dealt with the quadratic equation a little bit, kind of the roots of quadratic functions and what that means for us, stuff like that. So we're really just going to be reviewing all of those concepts and maybe introducing a few more today through our practice, which, like I said, is a really good way to integrate what we learned and make sure that we actually remember it. And also it gives you guys a way to get like clear perspective and clear introspection on what questions on the test are actually going to look like. Because basically what I did for these practice questions, picking them out for you guys, is I went through one of the harder ACT books and found questions that directly relate to quadratic functions, parabolas, all of page 8, so that you guys can see like what actual questions are going to look like, because they're not always going to be as simple and straightforward as, okay, find the vertex of this parabola. If it is, that's great, but they just have some different ways that they like to kind of test your knowledge over it, just to make sure you really understand the concepts behind it and not just that you're able to apply a formula, because that's typically a little bit easier. So, okay, without further ado, we're going to jump into some practice. For today, you're just going to need your math packet, the notebook that you've been working out of, definitely a graph and calculator, because we will work with that specifically a little bit today. But other than that, we're just going to go ahead and get started with some practice. Okay, so we have this problem up here, right? Just says graph the equation, gives us an equation. F of x is equal to negative, in parentheses, x minus 2 squared. And it wants us, obviously, to graph it. Obviously, related to an actual ACT test, you're never specifically going to have to sketch out a graph. However, what they did for this problem is this was like the exact setup, and then they had 5 different answer choices. So in that case, you could use strategies such as process of elimination. But for now, I'm just going to have you guys graph this. So yeah, I guess you guys probably have had time to write that down while I talked. So we're going to go ahead and go over the answer for this question. Okay, so there's a few ways to go about this. Before I get into the most efficient way, I'm just going to go ahead and kind of explain the reasoning behind it, because I think that's very important as well, because you're not always going to be able to use your graphic calculator for problems like these. So basically what I did is I kind of thought in reference to the basic standard quadratic function, where we have f of x is equal to ax squared plus bx plus c, where a, b, and c are all number values. In this case, it doesn't directly follow that format, however. So I'm still gonna be able to like think in reference to that format, but I am going to introduce another format to you guys right now. Okay, so this form that I introduced, you guys may not have seen it before. Still dealing with quadratic functions. It's the same exact graph, just a different way to write it, and we call this vertex form. Kind of self-explanatory as to why, you'll see why in a minute. So we have a couple different values for our vertex form compared to our standard form, right? I guess just to start off with, we have A, which in essence is gonna function in the same way that this A does up here. In terms of last time we talked about concavity and how quickly or how slowly our graph rises or falls, A is still going to do all of those things. So it's good to have that prior knowledge. But now we have the terms H and K introduced. So what do H and K stand for? H and K in a coordinate pair are going to stand for your vertex. So essentially, H would be your X term, K would be your Y term. So yeah, that's really going to tell us a lot about the graph. For the most part, that's what we're going to use to figure out this problem. However, there are some different ways of manipulation that we can figure out this problem as well. So we're going to go through all of those. Okay, so like I said before, there's a couple of pieces of information in here that I'm given. A, if I look, is actually going to be -1. Even though they don't write that in there, that's customary, just because you don't really need to. It's kind of like an invisible coefficient, but it is there and it is giving value to the graph. So our A is going to be -1. From that, we know a couple things. But the most important thing is that it's going to be concave down. So that's what our graph is going to have to look like. That's a big piece of it, obviously, so we're going to keep that in mind. Okay, so the next thing that I know from this equation, and specifically looking at vertex form, is that my vertex is going to be 2, 0. The reason behind that is because if you look up here, we have x minus 2, and this form down here is x minus h. So then if I were to look at it, you could look at it a couple ways. Either h is equal to 2, or if you do want to take that negative in there, you could say negative h is equal to -2. Cancel out the negatives, you're left with just h is equal to 2. So our h in this case is going to be 2. The reason that we have 0 for this is because there really is no k here, right? You could think about it this way, that there is a 0 here for that k. Regardless, however you think about it, it's not really going to have an effect because our k value is still going to be 0. So now I know 2 really important things. I know my concavity and I know my vertex. So I'm pretty confident that I would be able to sketch out an accurate representation of this graph. So just kind of like estimating. This is going to be about what this graph is going to look like. Again, our vertex is this point here, so I put it on 2, 0 on the xy coordinate plane, and then concave down. And the reason that it's not like stretched super skinny or super wide is because, like I said before, this term is going to be 1. So that's kind of just like the generic value for that A. So it's going to have about an average slope. Awesome. So that is that problem. Just introducing you to different ways to kind of think about how to graph problems. So done with that, we're going to move on. So this problem just reads as, find the sum of the two real solutions to x squared plus 3x is equal to 7. There are, I would say, probably like two good ways to go about this problem. However, one takes like substantially less time than the other. So we're gonna go over that one in a second. Okay, so we actually have a formula that we've been given for problems exactly like this, which is awesome. It's relatively simple, straightforward. We just need to know the formula and plug in the values that they give us. So the formula that we're given is pretty straightforward. It's called the sum of roots formula. And it looks very similar to another formula that we've already learned, right? Axis of symmetry, ring a bell? It's gonna be negative b over 2a. In this case, it's just negative b over a. So make sure that you keep those straight in your mind, but you could also use that to kind of help you remember this one. So yeah, all this is saying is that someone in the mathematical world found out this trend. Super helpful for us. We don't need to know how, we just need to know what it is and how to apply it. So we have our sum of roots. What that means is, if you remember when we talked about our roots last time, it's essentially where our parabola is going to cross the x-axis. So let's say we had something like this. Our sum of roots would be those two values added together, hence the word sum. But instead of like graphing it or individually finding both of the roots, which like I said before, can be more time consuming than just doing this, we get to plug this in. So if I look to my quadratic function, even though it's not in standard form technically, I don't necessarily need to manipulate anything around because a and b are both on the same side, and that's really kind of what we care about in this sense, because we're only dealing with a and b here. So my b is going to be 3, my a technically is going to be 1, negative 3 divided by 1 gets me negative 3 for the sum of roots. And that's kind of where we're going to leave that problem, just because the other alternative that we would have to solving this problem is, like I said before, finding the actual two roots. And the reason that that is going to be particularly difficult for this problem is because it doesn't factor out. So we'd have to do the quadratic formula, and then we would have to find the sum of those two terms of the quadratic formula. And although that is helpful in cases, we don't have to do it in this case, which is awesome. So yeah, that is that problem. Okay, so moving on to this problem, it just reads as if f of x is equal to ax squared plus bx plus c, and a, b, and c are all negative, sketch a possible graph. So kind of just like an intro to this problem, the ACT likes to do this a lot, where they don't give you absolute values. They kind of talk in a little bit more abstract concepts, like in this one. Like they're not giving you actual values for a, b, and c, right? They're just telling you that they're all negative. The reason that they like to do that is because you can't rely on like using mathematical functions, I guess, or using your calculator. You just need to know the general concepts, which in your case, if you do know the general concepts and how to actually apply them and the reasoning behind them, you're going to be totally good to go for these problems. Okay, so let's get to work with this one. So again, the way that we know that it's dealing with a quadratic function is because it straightforwardly tells us dealing with that standard form quadratic function equation. And it tells us obviously 3 important things. A, B, and C are all negative. So if we look at negative A, what that tells us, we know that it's going to be concave down, right? Just like our other kind of sketching problem, it's going to be facing down. And we're kind of going to overlook B for now, just because we learned last time there's not really one specific thing that we can learn from B itself without manipulating it in some way. But we are going to look at negative C. So negative C, if you remember, C itself stands for the y-intercept of our graph. So if C is negative, we know our y-intercept is going to have to be negative as well. So now I think that that's enough information for me to graph this. So I'm going to go ahead and do that. And I'm going to walk us through kind of that thought process. So again, I'm trying to construct a graph that is concave down. And I guess now would be a good time to introduce this concept as well. So there is technically a way that we can think about the contribution that B has to this problem, and that's going to deal more with the roots. So since B is negative in this problem, I know that we're going to have negative roots as opposed to having positive roots on the x-axis. That just deals with like kind of where the position of our function is going to be. So yeah, that is kind of the reasoning behind that. The reason, or the way that I kind of like got to that conclusion is just through, if you think about this from a factoring perspective, it becomes a little bit easier to say, oh, okay, I know I'm gonna need like negative factors in order to contribute to this negative number. So yeah, we're just gonna go ahead and get started. First thing I'm gonna do, because this is kind of like an easy function or an easy point on the function to graph out, is just make sure I have my y-intercept. And then from there, since I know I have my negative roots, I know I'm going to be working on this half of the graph and not this half of the graph. And I remember that it's concave down. So in the end, my final sketch could look something like that. It also could maybe just have like one root here. And I know that I am going to have roots itself because B exists. If B existed, I wouldn't have any real roots, maybe. It just kind of depends on the graph itself, but that is going to be one option for the graph. And then it was the same kind of setup as the other one, where it just gives you 5 different answer choices you have to choose. In this case, we got to work on our sketching skills a little bit. So that is that problem. Okay, so this is kind of a long problem, obviously going to be a word problem, but it just says a stone projected vertically upwards with an initial velocity of 112 feet per second moves according to the equation s is equal to 112t minus 16t squared, where s is equal to feet from the ground and t is equal to seconds, and it wants us to find the maximum height of the stone. So, logically, if we think about this problem, we know that it's going to be, again, a quadratic function problem, because it gives us kind of the basic format of that in that sense. So there's really one kind of main way that we're going to go about this. They introduced the concept of like graphing this. However, I don't think that that's necessarily the most efficient way to do it. So we're going to do the most efficient way. And the way that we're going to do that is employing a formula that we used previously. It's going to be the axis of symmetry, and we're basically going to work to find the vertex, because the value that we actually care about is going to be the y value, right? Because if you think about it, our y value is going to be our height in feet, and our x value of our vertex is going to be seconds. So we want that y value, so we're going to have to find the entire vertex. Okay, so if you remember, this is our equation for our axis of symmetry. It says x is equal to negative b over 2a, and all I did here was I just rewrote our original equation to put it more closely into standard form. So it says s is equal to negative 16t squared plus 112t. So now I'm just going to go ahead and plug in my b term and my a term into this and find whatever the x coordinate is for my vertex. Okay, so plugging that in, like I said before, negative b over 2a. Evaluating that in my calculator, I got 3.5 seconds. So, like I said before, that's the time, or the point in time, where we are going to have the largest y value. Now we just need to go ahead and find that y value. So, if you remember last time, the way that we found that y value is essentially just by plugging this x value. If you want to think about it in terms of s and t in this problem, that's totally fine. I think it can be helpful to just still think about it in terms of x and y, and just be able to like plug in the right term for where you're supposed to plug it in, because that's kind of just easier to see the relationship that time, or in that way. So yeah, like I said before, we're going to plug this value into technically our t value. In this equation, t and x are analogous in this situation. So yeah, we're going to go ahead and plug in 3.5 for t and get our s value out. Okay, so I just wrote this out. Obviously on the actual test, you do not need to write that out. I would just say to plug that straight into your calculator, this whole kind of mathematical sentence. But moral of the story is when we do type that into our calculator and we evaluate for it, we get 196 feet. So that is going to be the sole answer for this question. Okay, so I'll give you guys a little bit of time to think about this question, just because it's kind of on a different subtopic of parabolas, but nevertheless it is very important. It just says to find the solution set for the inequality x squared is less than or equal to 4. Okay, so you guys have had time to write that down. We're going to go about evaluating this problem. Okay, so like I said before, I'm going to walk you guys through the steps of this because we haven't really talked about it too in depth. So what I'm going to do is I'm going to subtract this 4 over just to get me equal to 0 on one side of the equation. That's going to be a common theme for just like quadratic functions in general, so kind of keep that in mind. We're going to be setting a lot of things equal to 0 in dealing with quadratic equations and quadratic functions. So then, when it says the solution set for this problem, it essentially just means all of the x values in which, if we plug it into this inequality, it would satisfy it. So in dealing with that, we need to actually evaluate 4 specific x values, just so we can kind of get like our parameters and find our range of values. So in order to do that, we're just going to go ahead and factor out. Works really nicely, this one does, just because it factors out perfectly. So yeah, if we want to break it down in this way, we can say that x squared minus 4 can be written as x plus 2 times x minus 2. If you want to think about it like specifically, that's dealing with difference of squares. So if you haven't already learned that, we definitely will be touching on that later. It is in the book, but it's kind of just like a, not necessarily a shortcut for factoring, but more just a trend that crops up quite often. So yeah, that's going to be our factored equation. Now that we have both of those two values, we're left with just 2 large values, the x plus 2 and the x minus 2 being multiplied together, right? So what we're going to do is just set each one equal to 0 and evaluate for x for each equation. Okay, so if I solve that down, I can see that x is going to be equal to -2 and 2. So what that means in the context of this problem is those are going to be our actual roots for our graph. So I'm going to go ahead and sketch that out. Again, this is obviously just kind of a rough sketch, but that's going to be our graph. So let's say hypothetically that in dealing with this problem, we were given x squared is equal to 4. In that case, we would only have 2 solutions, right? The ones that we just found. But in this case, we're not dealing with an equation, we're dealing with an inequality. That comes from the less than or equal to sign. So essentially what we're going to be finding is a range of values. So if we want to think about it in terms of referencing this problem that we just drew, there's really 2 solution sets that we have available to us, and we need to figure out which one it is. The first kind of option is it could be everything in between those 2 x values, right? Or it could be everything to the right of the positive x value and everything to the left of the negative x value. So really we have 2 options. We have everything in between the graph on the x-axis or everything outside of the graph on the x-axis. The way that I determined what this answer is going to be, you'll see in a minute, is actually kind of through like a cheesy acronym. Remember, it's not an acronym. I don't know what you would call it. Maybe like an onomatopoeia. I don't know. This isn't English. Not important. But nevertheless, it does help. So if we look at this inequality, it reads as x squared is less than 4, right? We kind of already established that. So I've, just kind of like remembered it through practice. But 2 kind of use, like I said, this cheesy remembering tool, where we have less than. The and in less than kind of sounds like and. So I know that this is going to be what we call an and inequality solution set. And that's kind of what I mean by this. So an and inequality solution set for this specific problem is going to look like that. That's actually our answer. But I guess kind of represented graphically, it's going to be the space in between those 2 points, not the spaces outside of these points. If it was the spaces outside of these points, it would have to be x squared is greater than 4. Oops. Again, kind of a cheesy remembering tool, but it works nevertheless. So we have greater, kind of sounds like great or. So that's going to be what we call an or inequality solution set. So the answer could either be over here, right? Or it could be over here. If one of the solutions to a solution set is over here, it can't simultaneously be over here. That would like be saying -5 is, or 5 is equal to -5, which we know it's not. So that's why it's going to be an or set. So yeah, this is the actual answer for this problem. Some of that other stuff is just kind of the reasoning behind it, and how to go about tackling other problems that look like this. So yeah, we're going to go ahead and move on. We have one final question, and then we will call it a day. Okay, so this final question reads as, which of the following represents an equation for which the sum of roots is -3 and the product of roots is 4? So again, this is kind of similar to the structure of the other questions that we had been dealing with, where it's going to give you actual answer choices. Obviously in the ACT, it's going to do that. But in this case, just try to kind of synthesize a function or an equation, if you will, based on this information. And then obviously it'd be a little bit easier if you are given answer choices, just because you can then check it, or you could use process of elimination and work it that way. Okay, so again, we are dealing with kind of similar concepts. As you see, they continue to crop up. And they are really all interrelated in this one larger category of quadratic functions in general. But what I'm specifically talking about is sum of roots, and we get introduced to a new term, product of roots. In essence, it's very similar. Instead of adding the 2 roots together, we're multiplying the 2 roots. Pretty straightforward. So yeah, if we remember, our sum of roots is equal to -b over a. And if you guys haven't seen this equation before, our product of roots is going to be c over a. So again, a, b, and c are all values in the standard form of a quadratic function. Now it kind of wants us to reverse engineer it. It gives us what the sum of roots is, it gives us what the product of roots is, and it wants us to synthesize that equation. So that's exactly what we're gonna do. So it tells us that our sum of roots is -3, and our product of roots is 4. Now, this is not necessarily a traditional equation, I guess. And in that sense, I mean, usually what they do if they want you to solve for a variable is they give you 2 of the values, right? And then 1 variable, and then you solve for the variable. Kind of backwards in this sense, we have 2 variables, 1 value. We can't necessarily isolate each of those variables, but we can manipulate it in a way to still find what those variables are. So in essence, what I'm gonna do is just set both of those values to 1, so that I'm kind of dealing with comparing fractions here. So if I look in this case, A is gonna be equal to 1 in both of those senses, which is great. I don't have to do any more manipulation with that. Therefore, if A is equal to 1, both of these kind of equations are gonna stay the same, right? So then B would be equal to -3, and 4 would be equal to C. So now I determined my A, B, and C values. I'm just gonna go ahead and plug that into my original quadratic equation, where f of x is equal to ax squared plus bx plus c So then, like I said, just transferring that information, I have f of x is equal to x squared minus 3x plus 4. Wonderful. Okay, so we are almost out of time here. Yeah, if I kind of had to wrap up everything I wanted to say about quadratic functions, just kind of reflecting back on the 2 different sessions that we had dealing with quadratic functions. A couple important key points that apply to a lot of other areas in math as well, but definitely apply here. Make sure that you're very familiar with the formulas. If you didn't know, for example, these 2 formulas here, you wouldn't be able to solve that problem. This is a relatively straightforward problem, doesn't take us too much time, so that would just be points that you're missing out on. So definitely memorize the formulas. Not only do you need to memorize kind of the formulas and the equations, make sure you actually understand the key concepts behind things. We haven't gone too in depth into it yet, but just make sure that you are comfortable with being able to factor, because kind of just factoring in general, not even related to quadratic functions specifically, is going to be a huge portion of the ACT. Just being able to manipulate mathematical equations in general. Utilize your graphing calculator whenever you can. Through all of these problems, we kind of worked through the actual mathematical explanation, which is great because I want to explain why things happen to you guys, not just how to use your calculator to get them. Because we even saw an example today where we couldn't use our calculator, and we had to use kind of our own knowledge. So that's really important as well. But your calculator is a perfect tool to use, so make sure that you're taking advantage of that. Other than that, I think that's really all I have to say about quadratic equations. So yeah, I will see you guys in the next video.